Welcome to a lesson with Dr. Powell. Let's talk a little bit more about the idea of curvature, which we represent by a Greek letter kappa. And we discussed that this was actually equal to the derivative of the tangent unit tangent vector with respect to arc length per unit arc length, as discussed in another video. Let's actually look at this quantity, which measures how much a path is curving. And let's look at what it looks like for a circle itself. For instance, what if we had something like this? T is equal to a cosine t, and let's use this notation, a sine t, where a is simply just some constant hanging out here. Now, this actually parameterizes a circle, x coordinate, y coordinate, of radius a itself. Okay, so let's try to compute this value for this particular function and see kind of what we get. So first off, we need to be able to compute t. T is simply v over the length of v. And so what is v? V is the derivative of r. So we can compute v as being with respect to t. So minus a sine t and a cosine t. Now, if you look at the length of v, notice this is you take the square root of this squared plus that squared. We're going to end up getting a squared times sine squared plus a squared times cosine squared. If you factor out the a squared, you're going to get sine squared plus cosine squared, which is 1. And then you take a square root to find the length. So basically the length is a. Let's just suppose that a is a positive number here. Okay, so basically we're just dividing by a. V divided by a will be t. Okay, so well, that tells us something. If you divide v by a, you know exactly what t is. It's just simply negative sine t cosine t. Very nice. Okay, so we got t. Now here we need to take the derivative of t with respect to s, but we're going to do it with respect to t instead and divide that result by ds dt. And this is the same thing as dt ds. Okay, so now what is ds dt? The derivative of arc length with respect to time is actually equal to the absolute value of the velocity vector, how fast we're traveling in the direction of the path itself is this, and it's also this. So two different ways of describing it. Okay, so we already know what this is. This is simply, we just talked about it here, the length of v is simply a. So pretty much all we have to do is take the derivative with respect to t and then divide that by a, and then we'll have this. And then we just find that length, and that will be the curvature. Okay, so take the derivative of t, and we end up getting negative cosine t minus sine t. So that's the derivative of t, but remember we just divide it by a, so 1 over a, and this is actually dt ds. So this right here is equal to dt ds. So we just need to find the length of this. Now, if you notice, the length of this vector right here, the cosine and sine, cosine squared plus sine squared is 1. Of this part right here is just 1, but then you multiply it by this length, 1 over a. So the overall length here is 1 over a of this vector, meaning that the curvature is simply 1 over a, which is interesting. A is like the radius. This tells us something. In general, when we have a curve, and we compute, maybe at a particular point, we compute the value kappa, which is the curvature. If we imagine that the curve is like a circle, then if we take the reciprocal of kappa, that should be kind of like what the radius would be of the circle that this momentarily is behaving like. So if you take this quantity called the curvature, you could say the radius of curvature is 1 over kappa. One more thing about curvature. If you take dt dt, and in another video we discussed this, so if you take dt dt and you divide it by its length, we end up getting what's called the unit normal vector. Well, this unit normal vector is in the direction of dt dt, but dt dt is also in the same direction as dt ds, assuming that mainly because if you look at this, what is ds? Ds is you could think of ds dt, and this quantity right here, you could think of it as being a positive constant here. And so really the relationship between dt dt and dt ds is very close. You're just multiplying by some positive constant here between the two. So if you normalize it here, you should get n. And so this should be true as well. This should also be n. And keep in mind, this is kappa. So by the definition, or curvature, by the definition of what curvature is, so we could think 1 over kappa times dt ds is equal to this vector. So we have multiple ways of describing what the unit normal vector is. Remember what the unit normal vector is. Unit tangent vector goes tangent to the curve. Unit normal vector, the derivative of this is, and then normalize it, you're always going to be perpendicular to the curve. So this would be t, and that would be n. Thanks for watching.